Okay, everyone. So this is part 3 of the scheduling video. There are two more techniques that I would like to talk about, and the first technique is critical ratio. So this technique generally helps with minimizing the job tardiness or lateness. The problem that you might say, okay, EDD does the same thing, but the problem with EDD is that it only considers the due date and it does not consider the processing time. Critical ratio is a technique that will have the same objective function as EDD, which is minimizing total job tardiness, but not only it considers due date, but also it pays attention to the processing time. So let's just look at this example and then look at this technique through one example. Let's say I have 4 products, 4 jobs to be processed, and I do have the duration of these jobs. It can be minute, hour, week, day, whatever. And the due dates are also given. So I do have processing time and the due date. So as you can see, this technique has an advantage to EDD because it also considers the duration of these jobs or processing times. So how does this technique work? Again, you do have the solution. Please don't do anything and just pay attention to the process of this algorithm. So first, we have job A, okay? So what you need to do is to see how much time you have till the deadline and how much do you need to spend on processing time. So for example, right now, the starting point of your scheduling, as we said, is time equal to 0. If I start at time 0, how much time do I have to the due date of job A? 20 units, okay? Do you agree that it will take 40 units of time to process this job? So 20 is the total. 20 minus 0 is 20, let's say, days that I have. Divided that by processing time, it give me a ratio of 1.43. You will follow the same concept for rest of the jobs and calculate a ratio of total available time divided by required time. So again, for job B, I'm at time 0. I have 16 days till then. And because I have not selected job A or anything, so I'm at time 0. I want to calculate this ratio for all the jobs. I have total available time is 16. 16 minus 0 is 16 divided by total required time, which is 10. So the ratio that we have, the critical ratio that we will have for job B is 1.60. The same thing for job C, the same thing for job D, which is 17 minus 0 divided by 6. Among these critical ratio values that are created, that have been calculated, you will select the minimum. So as you can see, among these numbers, the minimum belongs to job A. So I will start job A at time 0. It takes 14 days. So I will start with job A. So I have A, B, C, D. So the first job in this sequence will be A. So I will start it at time 0, and it will take 14 days to finish this job. So therefore, this a starting point of the second round to see what is the next job in this sequence. Should it be B? Should it be C? Should it be D? My time frame has updated, and right now I'm at time equal to 14. Okay, so now look at the remaining jobs. So how do I calculate the critical ratio? Is the total available time divided by their required time. So the due date of this job is time 16, but I'm already at time 14. Do you agree that the available time is 2 days? 2 divided by required time, which is 10. So the critical ratio will be 0.20. I will follow the same concept for C and D. For example, for D, the due date is 17. But I'm already at time 14. So available time till due date is 3 days. Divided by total required time is, for example, 0.5. Again, among these critical ratios, I will select the minimum. So it seems that C has the minimum ratio. So the next job in this sequence will be job C. So we know that the job C's duration is 7 units. So if we shift me to time 21, so my time axis right now is at time 21. Okay, so the jobs that I have already put in my sequence are jobs A and C, so make sure that they are removed from your set of jobs. And then we have to see what is the next job on this sequence. Should it be B or D after C? So I'm at time 21. So I know that the due date of this job was 16. So 16 minus due date, pay attention to the order, 16 minus due date, always the timestamp minus due date, divided by the total available time will give you the critical ratio of negative 0.5. And again, I'm at time 21, 17, the due date minus 21, it means I'm already 4 days late, divided by 6 will give you negative 0.67. So mathematically, which one is smaller? It seems that this value is smaller. So the next job in the process will be D, and automatically we know, I mean, since we have 4 jobs, we will see it at the end. So that is the optimum sequence of jobs that we have. So since I have A, C, D, B, I will just write it. I will just write the processing time, and I can calculate the total flow time, which is the cumulative flow time, which is 14 plus 721 plus 627. So then I add up these numbers. So as you can see, total flow time or total completion time is 99. And then for each job, I have also provided the due date. So how many days are we tardy? This job A, the due date was 20. The flow time or completion time was time 14. So I will not have any due dates minus that time is 0 because I'm not really late. But 15, for example, minus 21 is 6. So it shows that I'm 6 days late. Or for this job, 17 minus completion time, which is 27, is negative 10. It means I'm 10 days late. And then for job B, I was supposed to finish it at 16, but I'm at 37. So now I'm negative 21. It means I'm 21 days late. So the total tardiness or total lateness is going to be 37 days. So in case you want to calculate the total job flow time, you can, the average of whatever we have calculated, you have the total, for example, flow time divided by number of jobs, or total lateness divided by number of jobs. So just something so obvious that for average, you have the measure divided by total number of jobs. So that's what we call critical ratio. So really, as you can see, critical ratio, all it does, it calculates a critical ratio considering the time to due date, the updated time, probably I should say, the updated time to due date divided by processing time, And finally, you will select the minimum in each iteration, and you will continue until you are done with all the jobs. That is called critical ratio method. So, and again, as I said, it is appropriate to minimize job tardiness, and its advantage in comparison to EDD is that it also considers the processing time, because EDD does not consider processing time. EDD only pays attention to the due date and ignores the processing time, which is a deficiency of EDD. So that was it. So for example, I have compared the results of this algorithm with what I get from EDD technique and also what we got from SPT. So for example, if I have solved this problem, pay attention everyone, using critical ratio. Let me change my pen to highlighter. So total flow time using critical ratio, total flow time is 99 here. SPT gives you, EDD gives you 84, SPT gives you 79. And it's exactly what you should expect, because we said SPT goal is to minimize total flow time or total completion time, okay? Or the other thing is that look at the maximum lateness or total lateness. Let me just change the color, for example, to green. Look at here, the total lateness is 37 using critical ratio, total tardiness. For EDD, the total tardiness is 24, okay? And total tardiness is 24. So it seems EDD for this problem is giving the best answer. Look at the maximum amount of tardiness. Maximum tardiness using critical ratio is 27. Maximum tardiness over here is 17. For EDD and for SPT is also 17. It's a coincidence that they are the same. They're not going to be always the same. Okay, so just a comparison between output of the techniques. So if you want, you can solve the problems in this problem using SPT and EDD and confirm the answers that I have on my slides. So that was it for the critical ratio technique that was aiming at minimizing total flow time. Then the last technique that I want to talk about in this chapter of scheduling is the concept of flow shop scheduling. So for flow shop scheduling, I mean, for flow shop, you will have two jobs, for example, stations, two machines that are processing our jobs back to back. Okay, so it means the product first should go to station 1, and then it will go to station 2. This station can be a machine, can be a cell, or whatever. So something that I should tell you that, I mean, this technique can be very, flow shop systems can be very complicated. Just because it's just an introductory chapter to the concept of scheduling, let's just make the life easier. And I only consider two machines, okay? The technique that I want to talk about right now is Johnson's algorithm. So again, I want to talk about Johnson's algorithm to address a flow shop scheduling. By flow shop, it means that I will have only two stations, two machines that are in charge of processing the jobs. Job 1 will first go to station 1 and then goes to station 2. So the order is there, you cannot change the order. So the same as previous thing, for example, for SPT, we said our goal was for SPT, we said our goal was to minimize total flow time. Or for example, EDD, we said we wanted to minimize lateness. We wanted to minimize Lmax, or we wanted to minimize total lateness, or tardiness, another name for that. And for example, for the critical ratio, again, we said we want to, the same as in this one, we want to minimize Lmax or total completion time. So for Johnson's rule, our goal is to minimize make span. If you recall, make span was Cmax. It's different from total completion time. It's different from total completion time that we had before. So, we have calculated Cmax. We know it's the maximum completion time number in your system, okay? So, it also, at the same time, minimizes the total idle time between two machines, and also you should have several conditions. What are those conditions that we need, or those assumptions? Job time must be known and constant for each job at each work center. So you need to know how much time you need to spend to process job 1, for example, in a station 1, and job 1 in a station 2, job 10 in a station 1, job 10 in a station 2. You need to know how much time you need, and those numbers are fixed and they will not change. Job times must be independent of the sequence. So if you go with J1, J2 is the processing duration should not be affected if you have J2, J1. Job must follow same two-step sequence. So if job 1 is going through S1, S2, job 2, 3, 4, all the way to job N must follow the same sequence. And also all jobs must be completed in the first work center before moving to the second one. So it means that when job one is in this station one, first make sure that you will complete the processing. You're not going to send an incomplete job to the next station. So first complete the job in the first station and then send it to the next station. So this is called Johnson algorithm. So there is a algorithm like 1, 2, 3 step for that. So let's just briefly look at it, but it will be much easier to learn that technique through one example. So as you can see, it says that, let me just change my pen. So it says list the jobs and their times at each work center. Okay. Select the jobs with the shortest time, but if that shortest time belongs to the first work center, schedule that job first. Otherwise, schedule that to the end of the sequence. If there are ties, you can just break the tie arbitrarily. And you will eliminate the jobs that you have selected, which makes sense. And repeat jobs 2 and 3 working toward the center of the sequence until all jobs are sequenced or have been placed in the scheduling program that you have. So let's just look at one example. So as I said, Johnson algorithm is only for 2 machines, or 2 stations that are following a flow chart. It means that you are back to back. So a famous example that we always have for this field is the laundry operation. So when you have a laundry operation, you will first go from washing machine, you will wash, and you will go to dryer. Okay, so from washing machine to dryer. So you cannot change the order. All the jobs will, or all the products, all the clothes will first go to washer and then they will go to the dryer. Okay. Let's say I have 6 loads of laundry and the duration of the time to process each of these loads in washer T1 processing job 1, which is the time required to process load 1 in washer, and time to process the jobs in dryer is T2J. Okay, so T1Js are all these numbers. That's the time in washer. The last line is time in dryer. Okay, the question is that how should we sequence this? How should we sequence the jobs? Should I first go with laundry of 1, then 2, then 4, 5, 6? Or what is the sequence? What is the best sequence to do the laundry? So I would say I know I have 6 jobs that I have to place in my sequence. Okay. What was the algorithm telling us? It was telling me, hey, look at all the time durations. Okay. So all the time durations are provided here. Look at the one which is the smallest. If it belongs to the first station, you will put it at the beginning of your sequence. Otherwise, it will go to the end of the sequence. Among these numbers that we have for the duration of the jobs, among these numbers, which one is minimum, everyone? Which one has the shortest duration? Do you agree that 5 is minimum? That belongs to job 3. But time 5 is on the first station. Do you agree? 5 is minimum. That is on the first station. So since it's on the first station and it belongs to job 3, it shows that I will place job 3 at the beginning of this sequence. So just to make sure that I will not make any mistake, I will eliminate job 3 because I have placed that in my sequence. Then again, among the duration of these activities, among these durations, you have to look and see which one is minimum. Do you agree that 15 and 15 are the minimum? And they said if there is a tie, you can break the tie randomly. So let's say if I want to, for example, I said I choose randomly, I will select the 15 that belongs to job 4. So do you agree that it is on the second station, it is on dryer? So they said if that smallest duration belongs to second station, you have to place it all the way at the end of the sequence. It belongs to job 4, so I place job 4 at the end of the sequence. I place job 4 at the end of the sequence. So again, I'll come back to this list. I eliminate job 4. So again, among these numbers that are not crossed out, do you agree 15 is minimum? But it belongs to station 1. So I place it at the very beginning of this sequence. So I eliminate 1. Again, among the numbers that are not crossed out, what is the minimum? It's this 20 and this 20 over here. And they said if there is a tie, you can break this tie randomly or arbitrarily. So there is no rule. So let's say I will select this 20. It belongs to job 2, but it is done on the second station. So it means job 2 will go to the end of this sequence. So I eliminate job 2 to make sure I will not make mistake. So between job 5 and 6, I don't know, should I go with 5, 6 or 6, 5? We don't know what is the order. So I have to look at these processing times, the one which is not crossed, and look at the minimum duration. Minimum belongs to job 6 on machine 1 with the duration of 20 minutes. So therefore, I can say that I have to place job 6 first, and automatically the remaining job will sit afterwards. So 5 will sit over here. So that is the optimum sequence using Johnson's algorithm. So again, I will start with the minimum duration. If the minimum duration is on first station, you move to the beginning of this sequence. If that shortest duration belongs to the second station, you will put it all the way at the end of the sequence. So I know that's the optimum sequence in order to minimize make span or Cmax. So since I have done that, probably it's a good idea. We know that this is the optimum sequence that we have. So this Gantt chart is very informative because it is the outcome of your scheduling. So please pay attention because it's very critical. So for example, I can ask you to provide the Gantt chart for your scheduling problem. And that's what you need to do. At time 0, you will start processing job 3. You will process job 3, and how much time did you need? First, we always start with station 1. It goes from station 1. So job 3 on station 1 required 5 units of time. So I'll be done at time equal to 5. So immediately after after finishing the job in station 1, I can send it to station 2. On station 2, job 3, how much time does that need? On station 2, it will require 15 minutes. Look at here, 15 minutes is what you need on station 2 for job 3. So I have 15 minutes starting from time 5, and it goes all the way to time 20. So I place job 3 on both machines, first washer and then dryer. After that, for example, I place job 1. In job 1, for station 1 or machine 1 or washer, job 1 requires 15 units of time and 20 units on machine 2. So I will have 15 and 20. So from here to here is 15. And once I'm done, I'm at time 20. And actually, this is a good time that I can start processing job 1 on machine 2 because at 20, machine 2 will be available. The next job that we have is job 6. For job 6 and machine 1, we said it requires 20 minutes on machine 1 and 25 minutes on machine 2. So immediately I can start job 6, which takes 20 minutes over here. So I will be done at time 40. I place job 6. So we said I have to send it to machine 2, and it seems that, hey, this machine is done at time 40. So that's good. I can immediately start job 6. Then I have to place job 5 on machine 1. So job 5 on machine 1, if you remember, it requires 15 units of time. Job 5 on machine 1 is 25 and 30 on machines 1 and 2. So 25 will be here, and you will be done at this time for job 5. So you will be done at time 65. So I can immediately send it to machine 5, and we said that, and to, sorry, machine 2, and we said that you require 30 units of time. So it means that 30 units you will be done at time 95. Okay. So this is important, pay attention here. So I have finished job 5. Then the next job is job 2. Please pay attention. I place job 2 on machine 1. As you can see, I will start processing this. And for job 2 on machine 1, how much time do I need? It's 40 and 20 on machine 1 and 2 for job 2. 40 on the first one. So 40 will be 105. You will be at this time, 105. But once this job is over and I can send it to machine 2, I have to wait until time 105. So as you can see, between 95 and 105, machine 2 will be running idle. Okay, so I will be able to start processing job 2 because I have to wait until the processing in station 1 is completed. Then I can send it to this machine 2. So the gap that you see on the dryer between 95 and time of 105 is really the idle time for this machine. So for example, I can ask you, hey, what is the idle time, or in which period which machine is idle? You can look at this. So as you can see, as a result of this scheduling, I understand what is the sequence of the jobs and what is the operating schedule. So that's why we can technically really call it a scheduling. So Cmax, as you can see, the maximum time that the system will be released over here, the Cmax in this example is equal to 140. So that's the Cmax of this system, which is 140. So this is called Johnson's algorithm. So again, it is aiming at minimizing the Cmax or maximum completion time. And it's only for the cases that you have two back-to-back stations or flow chart. So with this, we will be done with the chapter of scheduling. Thank you, everyone.